Okay, here we are, first video lecture of the course. Take notes as you would in an ordinary in-person lecture in any other class. And I'll try to keep these short, but if you find that there's too much information coming at you too quickly, stop the video and take a break, come back to it a little bit later. We're talking about motion in the first few weeks, and the place to start when talking about motion is just how do you identify different locations that the motion starts at and ends at. Location we should think of as a vector quantity. As you saw in the reading, vector means some mathematical thing that has two aspects to it: a size, sometimes called magnitude, and a direction. Location is a vector. For example, let's think of one-dimensional motion, a case of one-dimensional motion where, of course, you assign a number to each point along that line, along that one dimension, and we'll say that the movement starts here at the 2 centimeter mark and ends here at the -2 centimeter mark. Initial location is a vector, something with both size and location. So when we say that the initial location is 2 centimeters, what we mean is that the size or magnitude, the absolute value, 2 centimeters, that tells you how far away this point is, how far away the initial location is from some reference point, and usually we just call the reference point 0 in most coordinate systems. The sign of this number, positive in this case, tells you the direction for this vector, and what that means, since this is a positive number, this vector points in the positive direction. That is, if you started at the reference point, you'd have to move in the positive direction to get to this particular location. And likewise, the final location is -2. The magnitude or size or absolute value of this is just plain 2, which tells you that the final location is 2 centimeters away from the reference point, 0. And then the sign, negative, means that this location vector points in the negative direction, which means that if you start at the reference point, you have to move in the negative direction to get to that point. So that's location, a vector quantity, but we're talking about motion, change in location, and the first quantity that we use when thinking about a change in location is displacement. We write displacement like this. Shorthand for displacement is delta x. Delta anything always refers to a change that happens over some period of time. And delta anything is always the final value minus the initial value of that thing. That the final value at the end of the time when you're watching minus the initial value at the beginning of the time when you're watching. So in this case, the final location is -2 centimeters minus the initial location, which was +2 centimeters, so that comes out to -4 centimeters. Delta x, the displacement, is built out of these two location vectors, so displacement itself is a vector. It's got a magnitude and a direction. Magnitude, size, absolute value is 4, and the sign, negative, tells you it points in the negative direction. What does that mean? Well, what it means is that the initial location was here, the final location was here, the magnitude of displacement tells you how far apart the beginning point and ending point are. That's the meaning of the size or magnitude or absolute value of displacement. And then the direction indicated by the sign, negative in this case, direction tells you which way you have to go to get from the start to the finish. The start was over here at +2, the finish is over here at -2, so you have to move in the negative direction to get from start to finish. That's what the direction of the displacement vector means. And as I've done here and here with these position vectors, you can always draw arrows to indicate any vector. Obviously, the direction of the arrow corresponds to the direction of the vector, and the relative sizes of the arrows correspond to the relative sizes of the magnitudes. This is about twice as long as this, and it's about twice as long as this, indicating that the magnitude of this displacement vector is 2 times larger than the magnitude of either the initial location vector or the final location vector. One thing to remember about displacement vectors, and I already sort of implied it when I said that the direction of a displacement vector points from the start toward the finish. I say it again here. The displacement vector points from the start to the finish. Just keep that in mind all the time. Now let's think about how to represent these location vectors and displacement vectors with arrows. You can represent any vector with an arrow, as I said. And in the reading, you saw that we have a specific way of talking about the addition of vectors. Let's say you've got one vector that's has a magnitude indicated by this length, and it points this way, call it A. And then another vector with a magnitude indicated by that length. This is about half as long as this, so the magnitude, size, absolute value of this is about half of the magnitude, size, absolute value of this. We'll call this one B. And let's say that we are adding A and B, and the result of that addition will be some new vector C. And to show the addition of any vectors, what's the rule? It's called a tail-to-tip rule in the text, and what that means is that you take the arrows that represent the things being added and connect them tail to tip. Right? The tip of the first thing in the sum is right at the tail of the next thing in the sum. And similarly, if you're adding even more things. So in this case, A plus B looks like that. And that makes sense if you think about A and B as themselves displacement vectors. A would be a displacement that took you from here to here. So this point here at the tip of A is the final location at the end of displacement A. But from that point, then you go through displacement B. And so the end of displacement A is the location from which you start displacement B. So the end of displacement A, the tip of A's arrow, is also the beginning of displacement B, the initial location, the tail of displacement B. This is the initial, this is the final location of displacement B. The initial location of displacement B is the same as the final location of displacement A. Now, the whole trip consisted of moving this way, moving through displacement A, and then moving this way through displacement B. So the very beginning of the whole trip that was constituted by these two displacements started there. There's the initial location, and there's the final location at the very end of the whole trip. So the net displacement, after going through displacement A and then going through displacement B, the net displacement starts here. This is the initial location of the net displacement, and there's the final location of the net displacement. The net displacement, as I wrote out algebraically here, the net displacement we call C. So those are our rules. Things that are being added connect tail to tip. And then the arrow that represents the sum, or the net result of that addition, starts at the tail, the beginning of the first arrow in the sum, and goes directly to the tip of the last arrow in the sum. Now let's see how that works in terms of positions and displacements. We had that movement from +2 to -2. If we represent it with arrows, the initial location is represented by an arrow pointing to the right, pointing in the positive direction, and its magnitude is 2 centimeters. And then the final location, -2 centimeters, is an arrow that's equally long because x final -2 has the same magnitude as x initial +2. And opposite signs, so they point in opposite directions. Okay, now the displacement is just x final minus x initial. It's a sum of two vectors. So if we want to show how x final and x initial combine to give you the displacement, we're really talking about summing together two vectors to get a net result being delta x, the displacement. Now, to be precise here, what are the two vectors that we're summing? X final, and then we add to that the vector minus x initial. And minus any vector just means a vector of the same magnitude but pointing the opposite way. So this minus xi would be represented by an arrow just as long as xi itself, but pointing in the opposite direction. And then let's add them together, tail to tip, to see what the result is. So x final, the first term in the sum, and then x initial is equally long and points to the right, so minus x initial has the same length but points to the left. And we're adding minus x initial to x final, so we connect the tail of x initial to the tip of x final, tail to tip. And that sum x final minus x initial, or x final plus minus x initial, is the displacement. It's the sum. Displacement is the sum of those two vectors, and you always represent the sum of vectors with an arrow that starts, remember what I just said a few minutes ago, at the tail of the first term in the sum, and then it goes directly to the tip of the last term in the sum. So this is delta x, which points in the negative direction, as we saw. The value of displacement is minus 4, points in the negative direction, and its magnitude is twice the magnitude of this or this, because these both had magnitudes of 2, and this had a magnitude of 4. Just another way of getting to the conclusion that we had already seen earlier. Okay, that's the basic idea, and we'll work with some of that in the next class.